So there's actually quite ingenious derivation we can do now that we understand scaling behaviors. And it's called Euler integral forms of the internal energy. And if you know anything about Leonhard Euler, you know that many of the things he did have this similar kind of ingenious quality to them. So let's see how this works. We're not going to do the total, all of them right now. We're just going to look at the Euler integral form for the internal energy U. Now remember that the internal energy is a special quantity in thermodynamics, right? It's related to heat, work, and chemical work for a system with one component. And notice here that the D's, the differentials, are only sitting on the extensive variables, right? Internal energy was extensive, entropy is extensive, volume and number of particles are extensive. The coefficients, T, P, and U, are all intensive. And that makes some sense, right? If we take a derivative here, say du ds, holding V and N constant, all right, that gives us the temperature. We had this derivative, way back when we first were working with entropy for the first time. And so even in these derivatives, we can look at whether quantities are extensive or intensive to check if they're going to work. So we have a ratio here, essentially, energy over entropy. That's a ratio of two extensive quantities. It's intensive. So temperature is intensive on the right side, and the equation works. But internal energy is special in another way, is that it only depends on changes in the extensive variables. Right, in the extensive variables. So what the Euler integral form does, it exploits the scaling relationship on this equation. All right, let's say U, internal energy, is a function of S, V, and N. This is true because of what variables appear in the differentials. And let's scale this entire equation by some scaling factor lambda. So lambda U is equal to this internal energy function with lambda S plugged in, lambda V plugged in, and lambda N plugged in. Right, so U with the parentheses is some functional form, and we're plugging in these three values. And then when we scale the system, we replace the left side with the scaled up energy, and we plug in the scaled up values to this function. So the function stays the same, but we plug in scaled up values. So what Euler did was he said, hey, let's be clever, let's take this scaled relationship and take its derivative with respect to lambda. Okay, so d lambda. Remember that U, S, V, and N, they don't depend on lambda themselves. The function doesn't have any special dependence on lambda, but the arguments do. So if we want to do this derivative now, we've got three slots in our function, and we have lambda in each one of those. We have to use the chain rule. So this is going to be the derivative of the function with respect to its first slot, right, the S, with V and N held constant, times the derivative of what's in the slot, lambda S, with respect to lambda. So that's the first term in our total derivative of this. We've got two more to go. It's du dv at S and N times the derivative of lambda V with respect to lambda. Oh, these should be total derivatives. There's no other dependence on lambda. And then the third term is du dn at constant volume and constant entropy times total derivative of lambda n with respect to lambda. Okay, so it takes this scaled equation and it takes the derivative with respect to lambda. So what good does that do us? Well, as you see these derivatives here, most of these derivatives that are left over now are essentially trivial, right? U, S, V, and N don't depend on lambda internally. So this derivative here is just going to be U. I'll leave these partial derivatives the way they are for the moment. This derivative here is just S. This derivative here is just V. And that derivative there is just N. So we get this expression for the internal energy. Again, we can be kind of going in circles here. But this is what Euler did with this kind of scaling relationship. Now, in the case of thermodynamics, we're in a special position to go a little bit farther here. These derivatives, du ds, they're not just brand new things, right? We kind of know something about what they are. Du ds with constant volume and constant number of particles is just the temperature. So this first term here is T times S. What about the second term? Well, the derivative of internal energy with respect to volume, well, entropy and particle number are held constant, is actually just equal to the opposite of the pressure. This is minus PV. And in the last one, derivative of U with respect to number of particles, that's just the chemical potential. So we get this beautiful looking equation that relates the internal energy to all of the thermodynamic state variables multiplied by their conjugates and added together or subtracted. So this equation looks great. Like, I want to find out the internal energy. Why don't I just plug into this? Well, it's a cute equation, but unfortunately, the more variables that appear in an equation, the less useful it actually gets, right? So to use this, I would need to know independently all 6 of these guys. So it's not great for doing calculations, but it is sometimes a way that you can get the internal energy, at least a formula for it, or get a formula for the pressure or something like that without having to go around the block and do a totally different method. So it is a tool in our toolbox, a relationship between quantities that we might have not expected. So this is called the Euler integral form. Of U. And it comes out just because of the scaling behavior of the thermodynamic variables, whether they're intensive or extensive, and it gives us this nice cute equation that relates all of the things we've talked about already. Okay. Now let's just do a sanity check and see how we might use this. Okay, so what's a system for which we know all 6 of these things already, so we can check this? Well, obviously it's going to be the ideal gas, right? Because none of the other things we've considered had pressure, entropy, and chemical potential all going on at the same time. So let's write those out as completely as we can. We know entropy was nR log of, what do we put this as? 2 pi m kt. So it's V over n. And then we have 2 pi m kt over h squared to the 3 halves. That's that. Plus 5 halves and bracket. We know the pressure is nRT over V. And the chemical potential, I usually don't remember this one off the top of my head, but I know that it's in this book somewhere. Chemical potential, ideal gas. It's got to be near the end of chapter 3, where the author defines chemical potential for the first time. All right, so I found it. It's equation 3.63. All right, so mu is negative RT times the natural log of basically the same stuff that's inside the log in the entropy. And that's it. Oh, this is a pretty bad looking Planck's constant there. That's an H, not an N. Set down the book. All right, so let's get rid of that. We know the name of it. And, let's plug these into here. So these are all in terms of volume, number of particles or moles, and temperature. So I've kind of arranged this so that I'll be able to simplify. Let's plug these all into the Euler integral form and see what falls out. So U is equal to temperature times this whole thing. So I'll have nRT. For this logarithm, I'm just going to write it as log of dot. So we all know what's inside the logarithm. There's no other logarithms anywhere else. So I'm just going to write this as log. That's the log part. I've got the 5/2 there. All right, so that's T times S. Let's subtract P times V. So nRT over V is the pressure multiplied by volume. And then let's add the chemical potential. So we'll add mu, which is negative RT. Oh, I really should have, I wanted to get it all in terms of R. But since I'm using number of particles here, I really have to do, this is chemical potential per particle. With R there, it's chemical potential per mole. So I'll leave it like this because I have the particles here, I have to use chemical potential per particle. So negative KT times N, and then the logarithm. All right. I think that covers it, mostly for the substitutions. And let's see if we can simplify this. Well, the first thing we know is that the internal energy for the gas doesn't have any logarithms in it, right? So we hope that that will go away. So here we have nRT times the log. And here from the chemical potential term, we've got minus nKT times the log. We know that nR, moles times R, and molecules times Boltzmann constant are the same thing. So these two guys cancel each other out. So that log and that log, this one's plus, this one's minus, those go away. All right, what's left over? Then we have 5/2 nRT from this first term, and minus, the volumes cancel there, minus nRT from that, the PV term. So 5/2 minus 1 is 3/2. And look at that. We get back to our internal energy formula, 3/2 nRT for the ideal gas. So if we haven't done the ideal gas to death enough, we've done even more here. We've shown that with the Euler integral form, we can actually plug these things in and prove that they work, at least for that case.